This is not really going to be an overview of LIGO because there's too much to cover. It's going to be an overview of just a handful of the core technologies that are what we call, I guess, the tricks of the trade. So I'll start by reminding you that everything in LIGO is driven by noise, and that means that every technology that we use is one that addresses a key noise source. So, for example, our suspended optics are aiming at reducing seismic and environmental noise. We have a seismic and environmental noise isolation system, which are seismic stacks. We have, in order to minimize phase noise along the light path, we have a vacuum system. We have methods for controlling the test mass thermal noise. We have a long effective arm length, and that improves our sensitivity for a finite laser power, and therefore finite shot noise limited sensing. We have a long effective arm length. We have low noise sensing electro-optics and electronics. This is what we'll call technical noise. And we have power recycling techniques for improving our laser power effectively. And an extremely stable laser, and that's because any noise associated with frequency phase fluctuations, intensity fluctuations, or in the transverse profile of the beam will produce noise. And I hope to help you understand some of these things, because they're just going by. Hope to help you understand some of these things a little bit better in this talk, but some things I'll talk about more than others. Okay, so I'll put some emphasis on understanding phase noise and what we do about it. So just to remind you that the goal, the technique for identifying gravitational waves in a LIGO-like interferometer is to look for the difference in phase of light traversing the two paths due to the presence of a gravitational wave, which changes the lengths, the differential lengths between the two paths by shifting the phase of the light in these two paths. And then a Michelson interferometer is a device which measures the phase difference between light returning from two paths in a photodetector. And that phase difference is tiny. It's on the order of 10 to the minus 10th radians. And that is the primary thing that drives at least the optics of LIGO-like interferometers, is being able to measure phase shifts that tiny. Of course, the longer the light path, the longer the phase shift, and so we want to make the light path as long as possible. But there's a limit to how long we want to make it. I'll explain later. This plot is to illustrate that, that measuring phase shifts on the order of 10 to the minus 10th radians has been done in benchtop experiments. This one is the MIT phase noise interferometer, and on the X scale is the frequency of a disturbance in the length of the arms, and the Y scale is the equivalent phase sensitivity in radians per root hertz. And here's 10 to the minus 10th. Here's the line is at 1.2 times 10 to the minus 10th, which is what they were able to achieve, except for all these lines of excess noise above that limit. And those lines limit your ability to detect gravitational waves at just that frequency. And they're usually due to electronics or electromagnetic pickup. And in particular, you could probably see, let's see, 60 hertz. This is 60 hertz. No, this is 600 hertz, sorry. This is 100 hertz. So this is 120 hertz and 180 hertz. These are typically multiples of the 60 hertz that's running in the fluorescent lights all around. And it's that's the kind of excess technical noise that LIGO aims to eliminate as much as possible. But even if you can't eliminate it, what it means is that over a very narrow range of frequencies, you don't have much sensitivity. But in the surrounding regions, you still do. So that's a key thing to remember. We increase the length of our arms. You can do it two different ways. There are delay line interferometers, which can take practical lengths and turn them into very much longer lengths. But in a delay line, you're limited in the number of bounces you can make. And in a Fabry-Perot interferometer, depending upon how you design it, you can make the number of bounces back and forth very long, turning, say, a 4-kilometer long interferometer into something that's more like, well, 100 times that, or several hundred times that. And so you learned a little bit about Fabry-Perot cavities in the last lecture, and I'll talk more about them today. So let's see. Let me just go through a few numbers about how to turn these kinds of Fabry-Perot arms into gravitational wave detectors. So let's start out by remembering that the Earth is very noisy at low frequencies. And so the first thing we want to do is filter out all that low frequency noise. We take our mass and we put it on a pendulum. And pendulums are wonderful mechanical filters. And they filter out motion of the suspension point very effectively, but not at the resonant frequency of the pendulum, only above the resonant frequency of the pendulum. I'll talk more about pendula later. So if you have a pendulum of length, 50 centimeters, then the resonant frequency is on the order of 100 hertz. Is on the order of 1 hertz. And that means that above 10 or maybe 100 hertz, environmental or seismic motion, just the motion of all your mirrors, is reduced considerably. And so this sets the band, the lower limit of the frequency band of LIGO.
Would you like Alan to fiddle with the other projector for a few minutes and see if we can get it working, or you want to stick with this?
I can stick with this unless people find this quality lousy. It's okay? Then let's stick with it for the time being.
Yeah.
What?
Well, no, he'll have to fiddle for several minutes.
Yeah, I imagine he would. Yeah, turn off those front lights maybe.
Yeah.
That would help. Projector power. No. Oh, sorry.
Is that all right?
Then you'd like some light back there, of course. So room lights here. Chalkboard on off. We can go like this and I can dim it. No, we can't dim it. What is the no, that's still no good. Sorry. Is this all right? Sorry. I know. Okay. So above 100 hertz that's the lower band, roughly. I mean, in advanced LIGO, it'll be more like 10 hertz. But above about 100 hertz, that sets the band of frequencies that we're sensitive to for Earth-based interferometers. That means wavelengths on the order of 3,000 kilometers. Okay? And that produces, of course, a very tiny strain. And what we measure is the shift in the phase. And the shift in the phase is 4 pi, well, it's 2 pi times twice the change in the length of the arms, divided by the wavelength of the laser. That's our sensitivity of a Michelson interferometer to phase is in units of the wavelength of the laser. Delta L is the strain times L, and so, of course, to measure very small, for a finite and fixed ability to measure phase shifts, we go to smaller and smaller sensitivity in H by larger and larger L. But you can't make it too large, because if you make the length larger than the wavelength of the gravitational wave, which is like this or longer, then divided by 4 or so, the gravitational wave changes sign while the laser light is still in the arms, and that cancels out the effect on the phase shift. So the light is still bouncing around in the arms, and the change due to H cancels itself. You start losing sensitivity. So there is some kind of an optimal length, and that optimal length is on the order of the wavelength of the gravitational wave you're targeting divided by 4. That's about 750 kilometers for this example at 100 hertz. That's not very practical, building an Earth-based interferometer of that kind of a length. And so, for a more practical length, we increase the phase sensitivity by increasing the number of bounces, the number of round trips of the light, by using Fabry-Perot cavities, or you could use delay lines. But a delay line, I don't think anyone's ever built a long delay line of laser light with more than 6 or 8 bounces. At least in that case, the bounces are well-defined. There's a well-defined travel time, a number of bounces. In a Fabry-Perot cavity, the number of bounces is a statistical thing, of course. Each photon bounces a random number of times, and on average, you can use the terminology of a bounce number to describe it. So that's the key to increasing our sensitivity for a finite length interferometer in the frequency ranges of interest. So let's talk about Fabry-Perot cavities, which are the arms of LIGO-like interferometers. So you work through. This is terrible. There are horizontal lines over here that are missing, and so on. I don't know. Looks fine on my screen anyway. You worked out these formulas for the circulating light, proportional to the incident light, but with a proportionality factor, this is a fraction, which can get very large when R1 and R2, the amplitude reflectivity of the input mass, or input mirror, and end mirror, approach 1. So when these approach 1, this denominator gets very small, and the light circulating in the cavity gets very large, and that means the light transmitted through the cavity gets very large. What about the reflected light? It's the reflected light that we actually use.
On your exercises for Wednesday, so those of you who haven't done your homework yet, here are some answers.
Giving you the answers. Terrible. But these are straightforward calculations, and they can get more complicated because this is the simplest case of a single cavity. And of course, LIGO has two cavities inside of another cavity, and there will be yet another cavity for advanced LIGO. And there are lots of cavities in LIGO. So it gets more complicated from here. This is the simplest case. If we look at the reflected light, it has that 1 over R1, R2 in the denominator as well. It also has in the numerator the difference. If we say that the losses are small, and we say that we're on resonance, so this is a multiple of 2 pi, then the numerator has an R1 minus R2, which could be 0, it could be positive, it could be negative. It depends on how you choose R1 and R2. And just to anticipate, in LIGO, we choose R2 to be as high as possible, and we choose R1 to be a little bit less so. And that means that R1 minus R2 is negative, and that's called an overcoupled cavity, and we'll talk about those in a minute. In any case, when 2kl is an integral multiple of 2 pi, then this quantity over here is 1, and this denominator gets as small as it can get. And that's resonance. And if you change either k by changing the wavelength of the light, or L by changing the length of the cavity, it changes that resonant condition. It's very, very strong function of the wavelength of the light and the length of the cavity, very close to resonance. In fact, by making R1 and R2 as close to 1 as you can, this can get exquisitely sensitive to the wavelength of the light or the length of the cavity. And so a Fabry-Perot cavity is a beautiful, if you like, filter, or it allows you to measure. It's an interferometer in itself. It allows you to measure lengths or frequencies with exquisite precision. Near resonance, again, there's a horizontal line. That's a ratio over there. The reference, this is the same formula that I wrote down in the previous slide for the reflected light, arbitrarily. But near resonance, I'm going to set 2kl close to 2 pi. And then I'll let L change from its resonant condition by just a little bit, delta L. And remember, delta L is very small in our case. And you get a formula like this. And what you see is that we can measure delta L quite accurately by looking at departure from resonance. And again, when this denominator gets close to 0, the effect is amplified tremendously. Okay? And this is a valid formula if 2 pi kl, 2 pi k delta L is very small compared with 1. And then what you see is you pick up an I here. And that I means that the amplitude of the reflected light is phase shifted. You get a little bit of light at 90 degrees phase shift with respect to the initial light. And it's that phase shift that we want to detect, because it's that phase shift that has information about the change in the light. The intensity, the reflected light magnitude squared, is mostly unchanged. And it goes like this delta L squared. And if delta L is tiny, then there's almost no change in the magnitude or intensity of the reflected light. It's the phase shift that has the information about the change in the length. So that's what we want to measure. And again, it's tremendously amplified by this thing in the bottom, in the denominator, which can get very, very large. And that's the bounce number, or it's directly related to the bounce number. Basically, is a statistical quantity that tells you how long the light is stored inside the cavity before it comes out, how much time it has to accumulate phase shift while the mirrors are moving, while the length of the cavity is changing. Now, if you imagine that this change in the cavity length is not a constant number, but is varying with some frequency, it's varying sinusoidally with some frequency delta L, delta F, where delta F is the gravitational wave frequency. Okay? Then instead of expanding this in delta L, let's expand it in delta F. And then this exponential in the denominator again picks up a phase shift, a 90-degree shift in the amplitude of the reflected wave. Okay? However, that's only true when this quantity is on the order is small compared with 1. Okay, because you're expanding this exponential. And that's no longer true when delta F gets to be as large as the so-called pole frequency, which is given by this formula over here, and which, when R1 and R2 get close to 1, gets very close to 0. In LIGO, the pole frequency is 90 hertz. And therefore, we start losing sensitivity to changes in length when those length changes are varying sinusoidally at frequencies larger than about 90 hertz. Okay? And that is the effect that I referred to 2 or 3 slides ago, that when the wavelength, when the frequency of the gravitational wave gets large compared with the storage time, or the inverse of the storage time of the light inside the cavity, you start to lose sensitivity when you're above the cavity pole frequency. So at higher frequencies, the interferometer response falls off like 1 over F. Okay? So this gives us a natural bandwidth. We saw that the environmental motion, seismic motion, gives LIGO and similar interferometers a lower limit on the frequencies it's sensitive to, on the order of 10 to 100 hertz. At high frequencies, it's this arm cavity pole that limits us. And in between is the bandwidth of LIGO effectively. Okay? You can do the exercise for any arbitrary configuration of mirrors and beam splitters and laser sources, and that'll define a set of static fields. And you can adjust all the lengths and positions such that the fields inside these cavities resonate. And that's your static case. In the absence of a gravitational wave, all the cavities, the laser light is resonant in all the cavities you want it to be resonant at, and not necessarily the ones you don't want it to be resonant at. And I'll explain what I mean in a minute. So that's the static case. And then a gravitational wave goes by. It's shaking a mirror. And if you shake a mirror, you can see that the phase shift, and I'm not showing this, but here's a mirror and here's light coming in, the light bouncing back is phase shifted due to the motion of the mirror. And that effectively, if the motion of the mirror is sinusoidal with a frequency f, then that's putting a sideband on the laser light, actually a pair of sidebands on the laser light, of frequency, the laser light frequency plus f and minus f, 2 sidebands. And those are called our signal or gravitational wave sidebands. And you can study the fields, not in the static case, but in this dynamic case where you're shaking mirrors. And you can calculate the fields as a function of the frequency at which you shake the mirrors, as long as you're shaking them by a very small amount, not so large that you fall off of resonance, but when you're very close to resonance. And we have numerical tools. There's a tool called Twiddle, written by a Caltech grad student who graduated about 5 years ago, which is a Mathematica notebook, which calculates the fields everywhere, including all the places where they exit the interferometer, where we can do our sensing of the motion of the mirrors, as a function of the frequency of the motion of any of the mirrors you want to shake. And that's how we numerically calculate how the interferometer acts like a transducer, transducing gravitational waves into phase wiggles of light coming out of the interferometer. Does that make sense? Does anybody have any questions about that? That's a core thing, and we're going to explore it more in a minute.
I'll give you an exercise to compute these things, dealing with sidebands for the next column.
Good. So I'll give you the answer. No. Anyway, let me just remind you that if you do have a simple cavity like this, then depending upon the R1 and R2, the reflected light could be 0, and that corresponds to on resonance, that is to say, and that corresponds to optimal coupling. That means no reflected light, all the light is transmitted. And that is a wonderful illustration of, the wonders of wave physics, because you're putting in incident light into a cavity, into a mirror, whose reflectivity is maybe 95%, and none of it is being reflected, because a little bit is getting through, coming back, and interfering destructively with the promptly reflected light, canceling it. Okay? So even though this a cavity like this, a mirror like this could be 95 or 99% reflective. You could have no reflected light. It can all be transmitted, or almost all transmitted.
So they have an exercise on that also for this week.
Great. And what you see is that if R1 is greater than R2, then then the reflected light is positive. If it's otherwise, it's negative. And those are called undercoupled or overcoupled cavities. And in LIGO, we want the light to come back with a flipped sign for technical reasons, which I might get into in this talk. But the arms are overcoupled cavities. In contrast, when I talk about the power recycling cavity, the power recycling cavity is designed to be almost optimally coupled. That is to say, all the light goes in and very little, almost none of it gets reflected. And that means we're using all of our laser light. We don't want any laser light to come back to us. It's wasted. A tiny bit comes back, that's our sensing light. But almost all of it goes in. Where does it go? Well, it can't actually be transmitted, because we make R2 very close to 1. So that only a tiny amount of light is actually transmitted. What we're really doing in a power recycled interferometer is we're sending light in, none of it is being reflected, none of it is even being transmitted, it's all getting stored in there until it all gets frittered away in losses, scattering and absorption. So we can build up the light inside of our interferometer. And in the absence of scattering and absorption, we can make the light in the interferometer go to infinity, which makes our response go very large. But of course, that's not the case. We're always limited by losses. And in fact, in a power recycled interferometer, losses are the most important thing that determines the sensitivity of your interferometer. I'll talk more about that in a minute. You last time learned about some of these concepts in optical physics. If you haven't heard about them before, the finesse of a cavity, which is the width of the. Let's see here. Here's the. Here is on the x-axis is you can plot several things. You can plot the change in the frequency f relative to its resonance, or you can plot the change in the length relative to the wavelength divided by 2. Either of those things is a change in a phase. Let's call this the change in the phase, which is delta phi divided by 2 pi. We'll call it delta nu, change in a phase or the tune. When you're at resonance, the field inside the cavity, circulating the cavity, gets very large. And if R1 and R2 are both very close to 1, the width of this resonance can get very, very small, making for a beautiful sensitivity to small changes in length or small changes in frequency. Okay? You learned about the free spectral range, which is the separation between these two things, which in these units is just 1, but you can easily convert it to units of wavelength, of frequency, or changes in length that way. Because really all that matters is the tune, the phase advance in a round trip around that cavity. So light storage time, again, when 1 minus R1, R2 goes to 0, the light storage time can get very large. These are the numbers for LIGO. The pole frequency can get very small. It's 91 hertz for LIGO arms as R1 and R2 approach 1. The cavity gain, that's the ratio of the electric field magnitude squared, the intensity of the electric field in the cavity, divided by how much is going into it. This can get very large. It's 130 for the LIGO arms. The visibility is another quantity that's worth knowing about, but I will skip it for now. And for the LIGO arms, the power transmissivity of the input test mass is 3%. The reflectivity, power reflectivity, which is little r squared, is 97%. And for the back mirror, we try to make it as close as possible to 1. The power reflectivity as close as possible to 1. Those are numbers for initial LIGO. They're a little different for advanced LIGO. Okay, power recycling. So the fields coming out carry that phase information, if we can only learn how to extract that phase information from the fields coming out. And those fields are electromagnetic energy, our laser light. And when the effect you're looking for, a gravitational wave, is really small, you get to the point where these fields are very, very low, and you're limited by the ability of your photodetector to detect them. And that is limited by the fact that the light that comes out is coming in discrete packets, photons, and the photons are coming in a little bit at a time over a for very high frequencies. You're opening up your window for a very short time and looking how much light goes into your photodetector, and you're getting to the point where you're counting individual photons. And then statistical fluctuations, Poisson fluctuations in the number of photons limits you. And that's shot noise. The power, the shot noise in your photodetector is white. It's independent of frequency. But the ability of your interferometer to transduce a gravitational wave at high frequency to the light coming out falls at high frequencies due to this bounce effect that I was talking about, due to this effect. Above the pole frequency, the transducer, the interferometer, is losing its ability to encode into the phase shift the motion of its test masses due to a gravitational wave. And so the shot noise is white, but the ability to measure a gravitational wave really falls off like 1 over f due to that white shot noise. Does that make sense? Does anyone want me to try to explain it better? Is it okay? Okay. So what we want to do is get lots of power into our interferometer. In order to not be limited by shot noise,